And we're going to get started on chapter 3 now, which focuses on alkenes and their stereochemistry. So, alkenes, alkanes, and their stereochemistry. So, hydrocarbons are defined as compounds containing only carbon and hydrogen atoms. Alkanes are known as saturated hydrocarbons that contain only carbon and hydrogen atoms and only contain single bonds. The alkane names end with an ANE ending. Is everyone okay so far? Is everyone able to follow along in their own set of chapter 3 notes from Canvas? Is everyone able to access their chapter 3 notes? Okay. Perfect, perfect. So the formula for a straight chain alkane is CnH2n plus 2, where n is the number of carbons. So for example, methane is CH4, ethane is C2H6, propane is C3H8, butane is C4H10. Now, what's really interesting is that the molecular formula of an alkane with more than 3 carbons can give more than one structure. So for example, C4 for butane, you can have butane and isobutane. So we can have butane, for example. And depending on how we arrange our carbon skeleton, we can get a range of different constitutional isomers. So from the same 4-carbon chain, we can draw quite a range of different structures. Likewise, for pentane, we can have pentane, 2-methylbutane, and 2,2-dimethylpropane. So 5 carbons, really the world is at our fingertips in that case, and we can draw a range of different possible structures with 5 carbons. So alkanes with carbons connected to no more than 2 other carbons are known as straight chain or normal alkanes. These can also be called linear alkanes. So for example, we call this chain here N-butane. And we'll talk about where we got the butane in a moment. It's based on the number of carbons. Does this make sense so far to everyone? Does this idea make sense so far? Any questions so far? Now, alkanes with 1 or more carbons connected to 3 or 4 carbons are called branched chain alkanes. So for example, this would be a branched variation of butane. So this is known as a branched species. Okay. So you're going to need to be familiar with the naming conventions for straight chain alkanes. So I provided you the names of common straight chain alkanes as a function of carbon count. We're next going to talk in detail about the rules for naming alkyl side chains and alkyl groups. So an alkyl group, otherwise known as an R group, replacing a carbon-hydrogen bond in an alkyl group chain with a carbon-carbon bond. So the way that we name an alkyl side chain is you look in this table and you find the prefix. So meth, eth, prop, but, pent, hex, hept. Each of these prefixes correspond to a carbon number. You find the prefix for your carbon number and you replace the ane ending of your alkane with the YL ending. So for example, CH4, methane, the CH3 group is known as a methyl group. Does that make sense to everyone? Does this idea make sense? You look up the prefix for the number of carbons, you change the ending to YL. So methane to methyl. Now, here are some common straight chain alkyl groups. So methane turns into methyl, ethane turns into ethyl, propane, propyl, butane, butyl, pentane, pentyl. 1, 2, 3, 4, 5 carbons. Each prefix corresponds to a unique number of carbons. Does this idea of naming make sense? Does this make sense to everyone so far? Any questions so far? Okay, we can build on this. We can build on this. So we're next going to talk about alkyl group classification. So alkyl groups are classified by the connection site of the parent chain. A primary carbon is a carbon at the end of a chain attached to one carbon. Secondary carbons are attached to 2, tertiary are attached to 3, quaternary are attached to 4. So we have our primary, secondary, tertiary, and quaternary. Likewise, we can label alcohols, hydrogens, and halides as primary, secondary, or tertiary based on and using, and this is really important, we are going to be using the carbon that our substituent is attached to. If our carbon is primary, secondary, or tertiary, we say that our substituent alcohol, hydrogen, or halide is thus primary, secondary, or tertiary. So let's show an example about how this can be applied. So if we're identifying hydrogens, notice how each of these 3 carbons are primary carbons, right? They're only attached to one other carbon. As a result, this hydrogen would be considered a primary hydrogen. Likewise, looking at this central carbon here, is this central carbon primary, secondary, or tertiary? Is this carbon that I boxed in green, is that primary, secondary, or tertiary? How many carbons is it attached to? 3. So is it primary, secondary, or tertiary? It's tertiary. It's a tertiary carbon, and as a result, this hydrogen would be a tertiary hydrogen. Just to make sure we're on the same page here, what about the carbon in blue? Is that primary, secondary, or tertiary? The carbon in blue is a secondary carbon, and as a result, this hydrogen would be a secondary hydrogen. Does this make sense to everyone? Is everyone comfortable with this idea so far? This is important because if a substituent is primary, secondary, or tertiary, it can affect its relative reactivity. So let's work on the following example and classify each of the following alcohols, hydrogens, or halides as primary, secondary, or tertiary. I'll do the first one. So this carbon is tertiary, it has 3 carbons attached. So this is a tertiary bromide. I'd like you now to take about 2 to 3 minutes and assign each of the following alcohols, hydrogens, or halides that I'll call A, B, or C as primary, secondary, or tertiary. and we'll discuss this example momentarily. So we already have one of our first assignments. Don't be shy to share your responses in the chat or any questions in the chat, and then we'll discuss this example in about another 2 to 3 minutes. And don't be concerned if your responses are different from that of your classmates. The more responses we have, the more feedback I can provide and the more supplemental examples I can design. And remember to pay special attention to the carbon that your substituent is attached to. The carbon that your substituent is attached to. So we're starting to see a reasonable pool of responses in the chat. So let's discuss these examples. So first and foremost, in structure A, looking at this carbon, it's attached to 2 other carbons. So we have a secondary carbon, and as a result, we have a secondary alcohol. In structure B, what is this hydrogen attached to? Let's circle that carbon. Now, is this carbon that the hydrogen is attached to primary, secondary, or tertiary? Primary. We have a primary carbon, and as a result, we have a primary hydrogen. Does that make sense to everyone? So remember, we only care about the carbon that our substituent is attached to. Likewise, for C, we have a primary carbon, and as a result, we have a primary halide. Does this example make sense to everyone? Do these examples make sense to everyone so far? Okay, so let's keep going. And let's talk about branched alkanes and alkyl groups. So a normal chain is known as an N-alkyl chain. When we have isoalkyl groups, our parent chain or carbon is attached to the secondary carbon. So N-propyl, our main chain is attached to the end. Iso, it's attached to the middle. Does that make sense to everyone? So to give you an example, this structure would be known as N-propanol because our alcohol is attached at the end. Well, if it's attached in the middle, it's known as isopropanol. Does everyone notice how the position of our main chain or substituent determines our naming? Does that make sense to everyone? Okay. Tert alkyl groups occur when we have 3 carbons attached to the carbon attached to the parent chain, or carbon attached to the tertiary carbon. So it's easier to see what's going on here if you look and you visualize. First, we have the N-butyl, which is our normal straight chain. Then we have the isobutyl. So in the isobutyl arrangement, does everyone see how we have a carbon attached in the middle? Does everyone see how we have this methyl group in the middle? This would be known as an isobutyl chain, just like our isopropyl example above. In the tert-butyl arrangement, as we notice, our main chain is attached to a carbon that is attached to 3 other carbons, right? That's why we call this tert-butyl. You can also think of it mnemonically as, if you look at a tert-butyl, it almost looks like a T. If you sort of look at it and squint a little bit, it looks a little bit like a T. Do these 3 butane chain isomers make sense to everyone? Is everyone comfortable with these examples so far? You are going to have to memorize and be familiar with each of these chains, as it's important when naming these compounds. Now, we can abbreviate isobutyl and tert-butyl as I-butyl and T-butyl respectively. Now, there's one other variation called a Cycloalkanes group, where we have 2 carbons attached to the carbon attached to the parent chain, or in other words, our parent chain is attached to a secondary carbon. Does everyone notice how we compare N-butyl to Cyclobutyl, otherwise known as S-butyl? We have moved our main chain from a primary to a secondary carbon. N just stands for normal. Yeah, nothing odd about it. Any questions on these different alkyl chains? So for the butyl chains, we have the normal chain, isobutyl, tert-butyl, and Cyclobutyl. Cyc, secondary. Any other questions on this? Now, when you're naming alkanes, this is a big topic now, and I really recommend that if you've downloaded and used the Marvin sketch from the class link, Marvin sketch has a tool that allows you to take any structure, and Marvin sketch will generate an IUPAC name for the structure. So it's a great way of generating problems on your own and checking your work. So when we name compounds following the IUPAC method, we follow a systematic process where we indicate the locant, which is the location of the substituent or functional groups, a prefix that tells us what are our substituents, our parent chain, which tells us how many carbons, and a suffix, which tells us our primary functional group. So here is the naming process for these compounds. First, we find the longest carbon chain. Now, this is known as the parent chain. If 2 chains have the same number of carbons, choose the chain with the most branches as your parent chain. So for example, we choose our longest chain that has 6 carbons rather than the chain that has 4. Because our main chain has 6, we name our main chain as a hexane chain. Now this can get pretty tricky when you have multiple branching paths. So in this case, we found that our longest chain has 7 carbons, and those 7 carbons beat out the 6 carbon chains, or our 5 carbon chains. So we find the longest chain with the most branching, and we name this as a heptane chain. Does this make sense? Does this make sense to everyone? Now, let's look at the following set of examples and let's identify the longest chain in each of the following. I'll do the first one. So I have a few options. First, I'm going to number from left to right. I have a 5 carbon chain. Okay, let me try numbering in red. I have a 6 carbon chain. Which chain wins out, 5 or 6? Yep, so I name this as a hexane chain, which is a 6 carbon chain. So this in turn would be named as 3-methyl-hexane. We'll talk about this more in a moment. So for now, I just want you to be able to identify the longest chain. So let's look at each of these 2 examples. You're welcome to use the annotate feature to circle the longest chain, or you can tell me the carbon count in the longest chain. And if you have any questions, don't be shy to ask them verbally or in the chat, and I'll be happy to get your questions addressed. And I'll label these A and B. I would double check the carbon count in annotation. You're on the right track, but I would just double check your count. And if you want, you can even number each carbon individually, if that would help. But the idea that you've presented looks good. And always think to yourself, is there a longer chain? And don't be shy to share your responses for the carbon count in the longest chain in each of these 2 compounds. And you may have to think creatively about how to number your carbons. And the response we see for question B, so then what's the longest chain? And you can change the color of the pen if you want to circle the longest chain in a different color. So we have a tentative assignment that the longest chain is right here. That looks reasonable to me. There we go. I boxed it in for everyone to see. Would anyone like to contribute a response for structure A? Would anyone like to tell us what is the longest chain in structure A? And we have a proposal that the longest chain contains 7 carbons in structure A. And really, I would encourage all of you to try grappling with these problems using the annotate tool and engaging with these problems using the annotate tool because the act of physically going through the problem solving process is invaluable to learning and engaging with the material. So the responses look great so far. The more practice you have on these topics, the faster you'll get at this. In general, my trick for this kind of method is I find the longest chain to start off with, like the longest base chain. So I see I have 2 3-carbon chains. Okay, so I'm just going to pick one of them to start with. So I put 1, 2, 3. So I'm starting from a 3-carbon chain, 4, and now I have a choice between 2 carbons or 3 carbons. And I want the longest chain, so I'm going to go down the 3-carbon chain path. So that gives us my longest chain as having 7 carbons. So this in turn would be named as 4-ethyl heptane. Does this first example make sense to everyone? Can I get some confirmation in the chat or verbally that everyone's comfortable with this first example? Where does the 4 come from? In this naming, in just this problem, you were asked to figure out the heptane, but the 4 comes from the fact that this ethyl group is at carbon 4. We'll talk about detailed naming rules in a moment. I'm just providing you the names so that way when you go back in your notes, you have more examples that have already been solved. Now, question B is a little bit tricky. So following my method, I've identified the longest chain. I see 3, 3, and 4. So I'm going to start from 4. Let's see, actually. So looking at our numbering, we have 1, 2, 3, 4, 5, and then I have a choice. 3-carbon chain, 3-carbon chain. It's a tie. I can pick, oh, sorry, this is not 3, this is 4. So I pick between a 3-carbon chain and a 4-carbon chain. I go down my longer chain, so 6, 7, 8, 9. So then our longest chain has 9 carbons. So then, as a result, this would be 5 propyl, and our carbon chain would be nonane. Does that make sense to everyone? You have to be really careful with your carbon counts. Sometimes you'd have to count your chain in a very odd way, not necessarily just from left to right. You have to find the longest chain, and the structures can be drawn in a way where you have to be really careful finding your longest chain. Do these examples make sense for identifying the longest chain? Is everyone comfortable with this so far? This is the backbone of nomenclature rules. Okay. So there are a range of different carbon chains, and they can have a range of different isomers. So let's look at some more complicated examples, and we have to identify the longest chain. So I'll do the first one and you'll do the next two. So first and foremost, I try to find my absolute longest chain. So I have 3, 3, 1, and 2. So I'm going to pick one of my 3-carbon chains. I'm just going to arbitrarily pick the top one. 1, 2, 3, 4. Now I have a choice between a 4-carbon chain and a 2-carbon chain. So I'm going to pick my 4-carbon chain. So 5, 6, 7, 8. Okay. So let's entertain some other possibilities. I can also count from the bottom. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and I'd get about the same result. So from what I see, my longest chain with the greatest amount of branching is an 8-carbon chain. And if we are naming this compound, this would be 4-ethyl 5-methyl octane. So our longest chain would be an 8-carbon chain. We'll talk more about where I got this exact detailed name once we're solid on identifying the longest chain. Remember, the parent chain is the longest chain with the most branching. So I'd like you to work on structures A and B and identify the longest chain. And really, don't be shy to break out the annotate tool. And just because one of your classmates is annotating doesn't mean you can't just draw the structure and show your own annotation. The act of working through a problem and physically writing out the numbers is invaluable to integrating the material. And remember, under meeting options, there's a little drop down. One of the options is annotate, and you can annotate on this class whiteboard. So we see some numbers for structure A. And this is where our rule about branching comes into play. So we have an interesting quandary to consider. I'm just gonna rewrite your proposed numbering with a different set of colors for structure A, as this really does deserve further study. So we have a marking method with black ink. Let's look at our numbering method with red ink. And let's look at a numbering method with blue ink. So, which method is preferred? Which method has the longest chain with the most branching? Which structure has the longest chain with the most branching? Which of these three numbering methods has the longest chain with the most branching? Red, blue, or the dark ink? Which numbering method? Let's try to get some responses in the chat for this. This is a very common trick question that can be put on exams to make sure people know their numbering rules. Yeah, the black ink, exactly right. Exactly right. So our longest chain, I'll circle it here, is this chain here. The reason for that, it has 1, 2, 3 branches, has the most branching in the main chain. So if we were naming we'd call this 3,5-dimethyl 4-propyl heptane. Let's work on structure B now, and I'd like you to identify the longest chain in structure B. And I'd like you to tell me the carbon count in structure B. And we'll discuss this example momentarily. So does anyone have any opinions for structure B? You're welcome to use the annotate tool to share your proposed carbon numbering scheme. So we have a proposal that the longest chain is hexane. That's exactly right. And we even have some students that are starting to try to name it. That's really good. And we have students calling this 3,4. Oops, did I miscount? Wait, this is heptane. 3,4-dimethyl heptane. Hept is 7, hex is 6. Very good, very good. So let's talk next about cycloalkanes. Cyclocyclic. Cycloalkanes are alkane chains arranged in a ring or cyclic structure. The cycloalkane is generally the parent chain if the attached carbon chains have less carbons. So cyclo is used as a prefix to indicate a cyclic species. So cyclopropane, 3 carbons, cyclobutane, 4 carbons, cyclopentane, 5 carbons, and so forth. Does that make sense to everyone? We'll see a lot of cyclic species next chapter. Okay, now this is where the rules, you really have to follow these procedural rules step by step. So carbons in the main chain are numbered in sequence. We put the substituents at the lowest carbon numbers. Substituents are identified and numbered, and you write each of the branches and substituents in alphabetical order before the base and stem name. You indicate the position of the branch on the main chain by prefixing its name with the carbon number. You separate numbers and letters with a hyphen, and you separate 2 or more numbers with a comma. ISO is considered a prefix and is alphabetized. And this is really important. Seq and tert are not prefixes and are not alphabetized. When a branch / substituent occurs more than once, you prefix the name with di, tri, and tetra. Then you list the number of carbon branch for that substituent to the name with a separate number for each occurrence. Okay, so let's look at this. So first, if we're dissecting the following example, first we'd identify our longest chain. So there are 2 counting methods. So we can either count from right to left or left to right. Now, if we look at our locant numbers, so we have numbers at carbon substituents at carbons number 3, 4, and 7, compared to substituents at 3, 6, and 7. So then, we go from the top of the line to the bottom of the line. So we both have locants at 3. Which number is smaller, 4 or 6? Which number is smaller, 4 or 6? Which locant number is smaller, 4 or 6? 4. That's why this counting method is preferred, because it has the smaller locant number in order of counting. Does that make sense? Now, our longest carbon chain has 9 carbons, so we name it as nonane. And then for each of our substituents, we note at carbon 3, we have a 2-carbon chain that we call ethyl. At carbon 4, we have a 1-carbon chain that we call methyl. And at carbon 7, we have another methyl. So at carbon 4, we have a methyl. At carbon 7, we have a methyl. So then, we'd write this as 4,7-dimethyl, okay? And now that we have all of our substituents named and numbered, now what we're going to do is we're going to consider alphabetical order in naming. So if we try to name this compound and we consider alphabetical order, we don't care about this di prefix. This di prefix doesn't matter. Let's focus on alphabetical order of methyl versus ethyl. Which is first alphabetically, ethyl or methyl? What is first alphabetically, ethyl or methyl? What does everyone think? Ethyl, exactly right. So then, ethyl goes first. So we call this 3-ethyl 4,7-dimethyl nonane. Does this example make sense to everyone? Does this example make sense? Does everyone see how all the pieces are starting to fit together? Perfect. So let's do some follow-up examples. So I'll do this one with you together. So identify and name all substituents in the following molecule and then name the parent chain. Ooh, this molecule looks like a bit of a mess, but remember, there's a fast method that I taught you. So you go to the ends of your chain, okay? And you find the longest side chain at each branch. So I have 4 carbons, 3 carbons. Oh, sorry, this is only 3. Oops. No, from our counting, all of these would be considered 3. 3, 3, 3, 2, 1. So I can pick any of these to start with. I generally pick the longest chain at the end to start counting from. So I'll count from the bottom just arbitrarily, and at each juncture, I pick the longest chain. So if I'm comparing 1 versus this giant chain, I'm going to go down the longer chain path. Likewise, if I'm comparing 3 to this giant chain, I'm going to choose my longer chain once again. Now at this juncture, I'm comparing 2 to 3. 3 wins out, so I go to the right. Okay, so I have a 10-carbon chain here. Another counting method would be to count from the top to the bottom. So let's write out my locants. So in red, I have a methyl at my 3 position. I have an ethyl at my 4 position. At 6, I have a propyl. What happened here? Whoops, this should only have 10. 7, 8, 9, 10. At 7, I have another methyl, and that's it. Now let's look at what happens if I follow the numbering method. In the black ink, I have 4 methyl, 5 propyl, 7 ethyl, 8 methyl. So just looking at my first number, you compare from the first number to the last. Which numbering method has the lowest locant numbers, the lowest carbon numbers for our substituents, starting from top to bottom? Which numbering method? Black ink or red ink? The red ink. So we're going to go with the numbering method in red. So here's our chain. Let's number it now. So we'd call this 4-ethyl, 3,7-dimethyl. Because remember, if we have 2 of the same substituent, we use a prefix. So this would be 3,7-dimethyl, 6-propyl decane. And if I punch this structure into Marvin Sketch, and I have Marvin Sketch tell me the name of this structure, we see that it's a perfect match. Let me just punch it into Marvin Sketch really quickly just to make sure. Let's see if we did this correctly. 4-ethyl, 3,7-dimethyl, 6-propyl decane. Exactly right. Perfect. Perfect. Now, before we close out today's session in the last 5 minutes, I'd like you to try to name the following compound, just so that way you have applied as our closing problem, you've applied the methods that we've learned today to name a relatively complicated alkane molecule. So let's spend about 3 to 4 minutes trying to name this example, and really don't be shy to go in with the annotate tool. It's all available through the tab as part of this Zoom call, and you really need to write out your numbers for both counting methods, because until you're more experienced with these sorts of problems, it's hard to do it in your head. So remember, we want the longest chain with the least amount, we want the longest chain with the most amount of branching. And we want the smallest locant numbers. And really don't be shy to share any questions you have or any proposed responses that you have in the chat or verbally. And just remember remember that your names should follow alphabetical order. But we already have some proposed names that look reasonable with a minor change. Let's keep working on this example for about another minute, and let's try to get a few more proposed names for this compound in the chat or verbally. Okay, so we see some reasonable responses in the chat. So now let's discuss. So we can find our longest chain pretty easily in this case because the longest chain is not particularly contested. If we number from left to right, we get a 9-carbon chain. Okay, so in the dark ink, we have a methyl at the 2 position, an ethyl at the 3 position, an ethyl at the 5 position, a methyl at the 6 position, and a methyl at the 8 position. Now in red, we have a methyl at the 2 position, a methyl at the 4 position, an ethyl at the 5, an ethyl at the 7, and a methyl at the 8. So which numbering method gives us the lowest carbon numbers from start to finish? So sequentially. So we have a tie at 2, but now which method gives us the smallest carbon numbering? The black ink, exactly right. So since we have 3 methyls, we call this, we have 3 methyls and 2 ethyls. 1, 2, 3 methyl, oops. 1, 2, 3 methyls and 1, 2 ethyls. So we'd call this 3,5 diethyl 2,6,8. Whoops, there should be a comma there. Trimethyl nonane. There we go. Does this example make sense to everyone? Any questions on this example? So everyone did great on this example so far. So that's the end of today's scheduled lecture.